Hi, my name is Milan Swart. I'm a master's student at the University of Pretoria and at Mintech, and today I'll be presenting the work that we've been doing on using a simulation-based approach to selecting a solar field site around a smelter complex. This work forms part of an EU project called PRIMA. There's an urgent need to reduce greenhouse gas emissions. The iron and steel sector is responsible for 23% of industry's sector's final energy demand, 66% of which is for process heat currently from fossil fuels. The PRIMA project is investigating the energy-efficient primary production of manganese ferroalloys through the application of novel energy systems for drying and preheating furnace feed materials. The PRIMA project is proposing to split the current submerged arc furnace smelting process into two stages, to include a pre-treatment stage, which is where heat from various sustainable sources will be introduced into the process. One of these sustainable sources being investigated is a concentrating solar thermal plant, which is the focus of this talk. More specifically, its solar field. Why? Because the performance of the solar field largely dictates the performance of the concentrating solar thermal plant's performance, and the performance of the solar field is mostly determined by the reflectance losses resulting from dust deposition. It is thus important to prevent as much soiling as possible, which is the focus of this work. Experimental campaigns were conducted, but the topic of this talk is the simulation-based approach, the goals of which was to use a computational fluid dynamics approach to simulate priority wind conditions at the study site, then to simulate dust dispersion using the discrete phase method based on the CFD results, and then to build a dust accumulation map, which can then be used by designers to identify candidate solar field sites. The first step is to obtain appropriately accurate terrain data, simplified versions of the smelter building complex, and then to generate a series of meshes for sensitivity analysis. The final mesh was built using the Fluent parallel meshing tool with 14 million polyhedral cells, which takes about 2 hours at the CHPC on 8 nodes. The first step to do with the final mesh is to perform a scaling analysis, and as can be seen, typical of CFD, more nodes equals faster compute times. On the right, the cutout is shown of the velocity field around the smelter complex at 2 meters height above ground level. An overview of the entire flow field is given here by looking at the turbulence intensity at 2 meters height above ground level. Very interesting flow features of the domain are highlighted. These CFD simulations are repeated for all the priority wind speeds and directions. Next, we can go on to simulating the dust using the discrete phase method. Initial scaling tests revealed that only increasing the nodes in an even amount results in better performance. On the right, a comparison is shown by releasing particles that are just following the streamline and using a random walk method to mimic the effects of turbulence in a steady state flow field. A dust source region is defined in the central part of the smelter building complex, and these dust dispersion simulations are repeated for all the priority wind directions and cases. A cumulative weighted map for a given sampling period is shown on the left, where it can be seen that there's local effects that the slag heaps have on the dust deposition pattern. There are areas of higher and lower dust deposition. The results were compared to experimental results, and the approach was validated because the simulation produced the same dispersion and accumulation pattern as was sampled, with some minor discrepancies. This information can be used to select an appropriate solar field site. Of the resources used, about 16% went to testing, 63% to setup and validation, and only 21% to the actual production runs. Thank you for your attention.